In this installment, we are going to look at centripetal force in vertical circles. And as we move through the course, we are situated here where we're dealing with forces, and we have a variety of different kinds of forces, and we have our geometric cases, inclined planes and circles. And so in this case, we're looking at forces as they apply to circles. In our last case, the vertical circles. In this diagram down below, you'll see that we have Mr. Einstein in the middle, and he got a bucket from his friendly neighborhood tractor supply company. And if he swings that bucket in a circle, it will travel at a constant speed. It doesn't matter if he has something in the bucket or not. If he's going fast enough, it won't fall out and hit him on the head. So what we have in this case, we are going to be considering a case where it's traveling at constant speed around the circle. And if we look at it from that perspective, we will focus on the centripetal acceleration, which is v squared over r. Now, I've just said that the velocity, the speed, we're going to work to keep it constant. And the radius of this circle is constant. So therefore, the centripetal acceleration is constant. And if we now look at the centripetal force, that's MAC. If AC is constant and the mass of this bucket, whether it's empty or not, has the same amount of material, it will be constant, and therefore the centripetal force is constant. And that's because we're traveling at a constant speed with a constant radius and a constant mass inside it. So the first thing I want to put in place then is that we are going to have a centripetal force that's constant throughout. And I will make that centripetal force red, the same color red we have there. And let's say that constant centripetal force is 25 newtons. So there's our centripetal forces. They are 25 newtons. Next, let's consider the weight of the bucket. Now, if I were to tell you that we put a half a gallon of water in there and 1 gallon weighs 8 pounds, then a half a gallon is 4 pounds. And to find out the weight of this thing, we would take 4 pounds, and we know that it's 1 kilogram is 2 pounds. So that's giving us 2 kilograms. And Fg equals mg. So 2 times 10 is 20 newtons. So we have a 20 newton force. Let's start over here at location 1. We have a 20 newton force of gravity. And here we have a 20 newton force of gravity at location 2. And at location 3, we have our force of gravity like so. And at location 4, we have our force of gravity like this, which is, and they're all 20 newtons. Well, let's now examine specifically what's going on with the tension. The tension, which we will draw in green, let's consider that in the case number 1. Now, the weight and the centripetal force are perpendicular to each other, so they don't interact. The only other force involved is the tension. So that means that the force of tension is 25. It's 25 newtons here. You could see that for the same reason, location 3, the tension will be 25 newtons. At the top, we could see if gravity is already contributing 20 of those 20 newtons, then the tension is only going to be 5 newtons. And then we can see that at location 4, that not only if our centripetal force, the net force is 25, we have to overcome the 20 that is going in the opposite direction, and so that the tension has to be 45 newtons. So algebraically, we could write these as, at location 1, Fc equals Ft. At location 2, the centripetal force is Ft plus Fg. At location 3, we have Fc equals Ft. And at location 4, we have Fc equals Ft minus Fg. Or in other words, the force of tension is equal to the centripetal force plus the force of gravity, or 45 newtons. And that is how we can apply forces in a centripetal situation with a vertical circle. So you could picture now if you had a lanyard with keys on it and you were swinging it around vertically in a vertical circle. It feels the heaviest. You get the greatest resistance to it when it's at the bottom. That's what you're feeling that resistance to. That's the tension. That's the tension that's necessary to both overcome the weight and change the direction of the tangential velocity to produce the centripetal acceleration. Similarly, as you are spinning that lanyard vertically, when it gets near the top, it requires very little. It feels very light, almost like it's not even there at all, because the tension is so small. And of course, then you can imagine that if we were to put water in these buckets, and we didn't want it to fall on our heads, we would need for the bucket to have an acceleration greater than or equal to 9.8 meters per second squared. And it's in that instance that the water will not fall on our heads. And that's vertical circles.